Welcome to the Place Northwest Masterclass podcast series,
where experts share their wisdom on key aspects of the property industry.
We're tackling everything from how to convert a listed building to the best way to hold a public consultation.
Don't miss a single episode. Subscribe now at placenorthwest.co.uk/subscribe
or wherever you listen to your podcasts.
Hello and welcome to the Place Northwest Masterclass podcast series. I'm your host, Julia Hatmaker, and I'm also the deputy editor at Place Northwest, and I'll be guiding you through today's episode. We'll be delving into the ins and outs of designing commercial buildings for science. We're going to go over the basics of what is needed for a science space, then we'll establish a few key tips and finish off with a real-life example of a project that really excels in delivering a science space that is also sustainable. Joining me today are two masters in the craft of designing science buildings, Fairhursts Design Group Managing Director Mark Adey and Director Laura Sherliker. Mark, Laura, welcome to the podcast.
Thanks, Julia.
Thanks, Julia.
So, Mark, can you tell us a little bit about Fairhurst's experience in designing commercial buildings for science?
Well, as a company that's been around for 125 years, our DNA really is in designing these for science. So, from our inception in 1896, which interestingly was when Marconi patented the wireless telegraph. So, for 125 years, this company uniquely has seen huge changes in technology, science, culture, the whole lot. And we've, as a company, have sort of ridden sort of side by side with that, designing buildings all the way through the years. So originally we started doing buildings out of the textile industry, dye stuffs, which sort of then evolved into the chemical industry. And then, through the 40s, aviation, into the sort of 50s and 60s, into university buildings, all sort of sciencey and industrial and manufacturing, and then into sort of big pharma in the 90s, to the point where now where we get to is we as a company work across the UK on a huge range of science facilities, from the very simple to the most complex that you'll find, national standard laboratories for very specific things. And for a huge array of different sorts of clients, more so than ever over the last 2 or 3 years, that the diversity of clients and people looking at the science sector, as it's become more and more at the front of people's agenda. Certainly through the pandemic, I think people have woken up to what science is all about. Some of us have been doing it for years and years and years and been excited by it, but the general population is now understanding actually it's quite useful to have scientists and people who are really interested in developing medicines and improving society. So as a company, we've sort of rolled through the years doing this sort of work, and then today we're really helping lots of different sorts of clients in producing buildings ready for a whole range of tenants, and certainly the range of commercial space, because there are now more and more tenants out there looking for space, looking for what traditionally you wouldn't have. 20 years ago, you weren't looking at you wouldn't have to develop space for speculative science tenants. It almost wasn't a thing in the UK, and then that's developed, and now today everyone is looking at the science sector as being an opportunity for investment and development, and then suddenly there's this idea of the commercial science facility, and how do you create something that we know and love in terms of offices? Actually, how do you create that for scientists? And that's what we've been doing. We sort of been doing it behind closed doors for years, but now it's very much at the forefront of what we do and what people are asking us to do.
Great segue. How is a science facility then different than your traditional office? Laura?
Yeah, no problem. The space needs for life science users are really specific and differ from others. The challenge is you can walk into a science space and think it's just like an office, and that's because on the face of it, it normally is. But it really, the complexity behind the building is hidden, and a lot of it you don't see. From the complex MEP installations and how the science will actually operate. Science spaces are generally built up of research areas where the science happens, and then typically have write-up spaces adjacent, which is like a traditional office where the scientists go and do their administrative work outside of the labs. Interestingly, these definitions are becoming quite blurred, especially as you go into the more commercial sectors and things happen differently, but you usually see it in some shape or form working in that sense.
Okay, so taking that into consideration, what are the basic needs of a science space?
I mean, write-up is obviously basically very, very close to a normal office environment. However, the labs are very different. Essentially, when we create those science spaces, we're creating environments that either protect the user or protect the research itself, creating a set of conditions for equipments or processes to happen specific to that science, be it highly clean spaces or dirty spaces. And that then comes down to how you deal with air pressures and things to control the flow of material and products and waste. It's all about how much air is required in the space, what temperature controls are required, the humidity, and it all needs to be very robust, cleanable, and safe when it comes down to the materials and products as well specified in those environments, because there's going to be lots of harsh chemicals used, for all of these different types of science that happen. And there are also spaces for people as well. You can't forget that whilst all the things that we've learned over the years about creating great workplace environments, we want to translate that also into labs, that they are places for people.
One of the things I'm sure people will want to know is what makes something lab ready. Mark?
Well, I think it's sort of fascinating, really, is that the terminology lab ready is sort of developed. I think it's developed quite recently as a way of trying to describe the ability of a building to accommodate science, whatever that might be. And there is a little bit of a trend where effectively any building could be described as lab ready. Just depends on how much time, money you have to invest in it to make it actually deliver science space. But we try and use it as a little bit more of a robust term in terms of being able to describe a building that has been designed in such a way that it can accommodate the sort of additional needs of creating these environments that Laura talked about. In terms of how we do that. So traditionally or typically where we talk about a lab-ready building, it's got things like riser spaces, so the ability to move air up and down the building. It's got things like goods lift because material movement through a science building is important. It's got the ability to be able to have lots of drainage because labs tend to be wet in the sense of having sinks and things like that. And you tend to also find structural issues being important. So you're concerned about how much vibration is transferred into the structure and how much the structure moves around. So and then things like a lab space needs lots of gases and lots of waste coming in and out, and then consumables. So it's got a big service sort of area. So you tend to find all these factors are added in, make it very different to an office, and put quite a different sort of pressure on how you develop a building. And you tend to find that where offices are described as sort of very efficient net to gross areas and all that sort of good stuff, we find labs are not as efficient, and we have to kind of educate people as to, you have to understand that you can't develop a lab buildings have so much extra stuff that you need to do. Is efficiency is slightly different. So in terms of lab ready buildings, it has these certain characteristics that mean it's ready to go. It doesn't necessarily have to have all the equipment in it or all the plant or all those things, but it has these qualities in it that mean that it makes it very easy to develop. And we're seeing there's an awful lot of work going on in terms of looking at existing buildings and how they can be developed for science. And some of those qualities you're looking at in terms of that existing building as to whether or not you can create riser space and put a goods lift in, or does it have one already? And so you find things like large format retail developments, they tend to have sort of similar qualities, and which make them very, very good for change, sort of moving over into a lab use. But then you might look at certain offices, and they can be quite tricky to do because they're very much designed specifically for that one use. So that to us is what lab ready means in terms of how easy it is to then turn it into a lab in the future. And of course that's good for the whole sustainability side of things as well, because we should be going forward making sure these don't design buildings that are too tightly focused on a specific use.
Okay, so I feel like I have a grasp on the basics. Now I want to get into the things you need to know. I want to design a commercial building for science use. What is one thing that I need to know? Laura?
So I think there's what are the basic and universal requirements for science space. So things that it has to be flexible and adaptable. That's because like science is ever changing, the avenues of exploration continue to expand. So those specific needs of life sciences are ever changing as technology, as equipment changes. So, being adaptable to those ever changing needs of the scientists and the research is really important. How you control those environments, as we've mentioned before, to do with air, temperature and humidity, again, relative to the unique environments that suit the science that's going on. Lots of access to power, data, flexibility with how you can plug and play equipment, how you can move it around, and the load requirements of that equipment. And therefore, to do that, large floor plates, so large floor to ceiling heights, and also, a good grid structure that allows for bench positioning to change, all those specific kind of principles for that the human kind of interaction with the benching and that configuration relative to the metrics of the human body. Really important, again, is to do with like clean and dirty regimes, to do with waste materials, so bringing new products in, taking products away, and the crossover of those, but also how you deliver goods to the building and how you move it around the building safely, given that you've got quite hazardous materials as well. And then drainage. Fundamental, the principles of drainage. You need kind of lots of drainage. You also need to consider what's being put down drains, so it's not getting into, water courses, and, larger kind of science clusters have specialist detection to make sure stuff doesn't go into, our kind of drainage systems that ultimately then go back into us, and those specialist services. So extraction, gases, hazardous chemicals and biologics are all those universal requirements that you've got to get right to make buildings flexible for science.
I mean, it's really interesting. What makes it a sort of fascinating job and a fascinating area of architecture is the rapid change of technology almost on an hourly basis. So we're working. We did a job down in Cambridge where we were developed space for DNA sequencing. And then if you just look at that technology, a process that took years to understand how to do it, and then originally the kind of kit that was developed filled the room and took months, now takes minutes and sits on a bench. And what's really fascinating is the timescales that construction works in. So design and construction, it can, a modest building can take, a year to design and a year to build. Technology's moved on. So there's a real challenge about how you develop space and design space, because the things you're designing for today won't be like that tomorrow. Once upon a time it was a piece of kit, now it's an app, and that's the kind of challenge and what makes designing these spaces really interesting, and why going back to flexibility and adaptability is really key, because everything's changing.
And I imagine that kind of plays into the fact that you don't want to be too specialist then in how you design a building, because you do need to be, as you said, flexible, because you don't know what the tenants of tomorrow are going to need.
That's utopia. That is the trick, and that's where I think we are incredibly good at what we do, in the sense of trying to resist the urges of the user who the scientist, the user is looking very much at the very specific, because that's actually what they do day to day. That's how they work. That's how they think. And we have to make people step back and go, actually, no, just let's think about how this might work from a long-term strategy and how this space could adapt. So simple things like try not to put a sink in the middle of a space that's really hard to move in the future. Put it at the outside edge of the space, which means the space becomes more adaptable. But it then goes back to your fundamental principles that we were talking about earlier, is getting those fundamental principles of the building right. So a good structure, a good floor to floor height, all those basics that are really hard to put in later on actually make the space long term, in a long term basis, very adaptable. And then that goes back to your sustainability agenda, where actually if you put in some simple strategies and make it really robust, it hardwires in that adaptability. And that's why you can see certain buildings Victorian buildings that are finding multiple different reboots and lives, because actually some of the basics were already hardwired in because of the way they responded to the technical challenges of the time.
Laura, when you were telling us earlier about all the drainage systems and how you have to get that right and you have to watch airflow, it just feels like science is quite strict in terms of building guidelines. Is that right?
Yeah, definitely. I mean, there's lots of legislation and guidance that has to be followed relative to the different types of science, whether you be dealing with pathogens or you're dealing with electronics. Again, the guidance documents that are there that you would lean towards are very different relative to those different kinds of science. So yeah, it's really important to be kind of abreast with those and the ever-changing requirements of them as well.
You all have mentioned how different sciences require different things, like life sciences have different requirements than those that are chemistry labs. So I imagine one of the key things to know is who you are designing for.
Yes and no. Yes, ultimately, yes. Ultimately, the science, the process is fundamental to the design of the building, and depending on the discipline and depending on what they're doing, will very much dictate the kinds of spaces. So, if you're talking about developing a drug that's going into people, that is very different to a space where you're looking at something to do with plant technologies or something. So that they are very much, this is what makes it interesting and what means it's not an office where, an office is designed for relatively simple activities. A laboratory can be used for so many different things. And the nature of research and development is science isn't just about one discipline. The innovation is actually where lots of these disciplines come together and where they overlap, that you get sort of the innovation. So you've kind of, so in many ways it is very specific, but in terms of bringing it back to how we design commercial labs, what you're trying to do is create a sort of generic level of specification that allows people then to build on that and to adapt it to their bespoke needs. And again, it sort of all circles back to that sustainability agenda as well, is get the basics right and then you can adapt it. What we're trying to avoid is going so far that then the incoming tenant goes, it doesn't work, I've got to rip it all out. So, and that A, isn't sustainable, B, is expensive. There's so many things that are wrong with that. So you need to take it to a certain degree, and we have developed specifications that allow us to get a reasonable generic specification that will work for most tenants. Certainly the smaller, less mature tenants, which then can be built upon and adapted. And we've got a number of buildings. Certainly one of the first UK science incubators that we did about 25 years ago, that's been adapted over time. But the basics are still the same in terms of the kind of canvas that we gave the tenants. They've adapted it, but it always goes back to the same sort of specification. And then you also need to wrap into the whole thing about who you aiming these commercial facilities at. Smaller tenants, young tenant, young companies that taking their first steps into commercialization and idea. They tend to be really, really easy to cater for, in the sense that they're quite They just want a little bit of space to develop their ideas. As those companies grow, there is a tendency for more bespoke space and more complicated space as they develop their ideas and as they bring in more technologies and things.
So it strikes me that the things you need to know when you are approaching converting an office building, a commercial building into a science one, the key is making sure you get the basics right when it comes to drainage, following all the guidance, make sure there's proper air ventilation and all like the security things are done for safety reasons. You also need to make sure it's flexible because you don't know how the future is going to be and what the science means of the future will be. And then you also kind of need to chat a bit with a potential tenant, kind of get an idea of, the basic needs there. Are they an incubator? Are they something bigger? That kind of jazz. Is there anything else people need to know?
I think, we've mentioned it, the same thing, that guidance, we've got to understand the hazardous nature of the space. How are they using the space? Are they simply wearing a lab coat, or are they sealed in protective suits and equipment? And really then follow those regulations that manage those hazardous environments. Understand the kit that they're putting in the building and how complex it is and how it's got to be either clean or dirty environments. And really then that then goes hand in hand with things like the plant room and the riser space that's required, because, very different to other building, the projects that we do, somewhere between 20 and 50% of the building could be taken up by plant, which again is very unique to this building type and science generally.
It's not just about creating some space for a scientist to work in. It's about creating an ecosystem within a building that multiple tenants can work with.
All right, so let's take it up a notch. Mark, you've been teasing continually throughout this podcast sustainability. It's been your favorite word. I have been paying attention to that. I want to talk to you a little bit about one project you guys did. 2016, the GlaxoSmithKline Centre for Sustainable Chemistry. It won the Physical Sciences Building of the Year award the next year from the S Labs conference. It's LEED Platinum, LEED Platinum, BREEAM Outstanding. It's supposed to be like the first carbon neutral lab in the UK. How did you do it?
It came out of GSK as an idea, as a series of ideas. Started as a proof of concept. 7 years later, it was a building on the University of Nottingham's campus. Slightly different idea, but conceptually the same. The same point about designing a building that effectively paid back its carbon. That was the brief. Very simple. Give us a chemistry laboratory. And if we go back to what we were talking about before, chemistry laboratories tend to be far more energy hungry because of what you're having to do in them. So you're talking about almost the most energy expensive building you can think of, and actually you're going to try and make that carbon neutral in today's terminology. But the terminology we were using was that it actually paid back its carbon over a 25-year period. And effectively, every design decision, every normal thought that you have about putting laboratories together had to be challenged as to how much you were spending, both in money terms, in cash, and in carbon. Because the whole point is you try to design a building with as little embodied carbon as possible. You're a net generator of energy. And then through offsetting from grid electricity, the theory being that you pay back the carbon that you've borrowed when you were building the building. That's the sort of concept. But what it means is you are looking at every single nut and bolt in terms of how it's made, where it's made, where's the source material, how does it get fabricated, how does it get to site, and trying to balance conflicting requirements. So you take a window, we want lots of natural light. That means we don't use as much artificial light. Great idea, massive windows, that works great. But hold on, you've got a potentially issue with overheating. So you don't want to do that. So you want to moderate the size of the window. But then glass is really carbon intensive. So actually, you're spending a lot of carbon cash, as it were, on that window. So it makes you think about everything, and we literally thought about every nut and bolt, and actually talking to suppliers about how they can take some of the material out of some of their products and still achieve the same specification. Laboratory furniture, where I think they took something like 20% of the steel out of it without it impacting on its base specification to the point of going where's the stone fill coming from for the ground floor slab, which quarry is it coming from, because that's really important. And in fact, when the building was on site, the contractor did so well in terms of understanding the problems and developing this building, but they were left with issues of, right, we need this stone fill. We can get reclaimed stone, but it's from 150 miles away, yet we can get freshly quarried stone 25 miles away. What's the right choice? Well, actually, the right choice was freshly quarried stone in that case, because it was nearby, and the kind of carbon credits they were having to spend to get it there. That was how you made it balance. So it was really made you think about everything.
I really like the quote about the client come back and said it's more than just a building, it's a whole philosophy. And that's when you really take it into then the operational side, and when the building is in use. And in order for the building to perform, the client had really bought into the process. So you hear these buzzwords like soft landings, and that's all about educating everybody that comes into the building thereafter on how the building should use, and how you minimize energy usage, and how nighttime cooling works, and understanding the relationship of turning lights on and off, and when windows should be opened. And it really embeds that into everybody's thinking, from the cleaner to the receptionist to the scientist to the manager within the building. So I think what's really great about that project was how everybody in the client team bought into net zero carbon, and what that actually meant. And its success is that in use, people are really kind of embedding that into everything they do.
So it sounds like if we're going to have a sustainable lab building, everyone needs to buy in, and you really need to take time to consider every little aspect of that. I do want to ask you guys about one of those, though, because we've mentioned repeatedly how important ventilation is. And I know when it came to this building, it was described as wind-driven ventilation. What does that mean?
Well, it's not a new concept. The basic premise was actually just try and make the building utilize any prevailing wind that might be available. And the concept that came out of GSK was to use a lot of the wind-driven ventilation, wind-driven assistance to the ventilation systems. Actually, as that got developed, as we developed that, and particularly when we moved it over to chemistry, that became more and more of a challenge about how you create that environment in a safe manner that we know is going to work day in, day out, not just on a windy day. But it's really, if you sort of strip it back, it's about looking at your environment and looking at how you design a building, and how you try and design that building to get the best out of what you've got. So, if you're in a hot, sunny climate, that's different to being in a wet, cold environment. It's the basics. It's what we go to university for. It's what we spend years learning about, is how it is designing to all these factors. On the Nottingham project, it was very, very, very much about the environmental factors that it was responding to, rather than any other contextual factors.
Now, for anyone who hasn't actually seen a picture of this building, I would advise you to go Google it. You'll see right off the bat some of the ways that you guys helped, cut the carbon costs and emissions. It's largely timber and CLT. Am I correct?
Yes.
And there's a wildflower blanket roof as well. And then how did you go about actually ensuring that it could generate energy to the extent that it could export it?
Again, it's about building forms that respond to the needs. So we basically fundamentally just needed a lot of PV. So that created the basic form, and that was something that came through from the original proof of concept. Is that kind of the volume shape of the building needs to have a lot of it effectively facing south. And then, as part of the university, and because they're on a campus, they were able to say, well, we can use a biomass CHP, which we probably wouldn't use now, but at that time was a good choice, and that allows them to actually create some heat export to some neighbouring buildings, and that allowed us to know that we could overgenerate, be a net exporter of energy.
And are those principles that you guys can take forward to your other buildings that you guys are designing, Laura?
No, definitely things that we can take forward. I mean, the GSK one is obviously unique, because of its site. It's very much a groundscaping building, and often you don't have that in urban context. So, we are doing things a bit differently in the likes of Manchester, out at Alderley Park, and in Liverpool in much more urban conditions, because you have to address the surroundings. But I think a lot of the principles and the approaches and the methodology from GSK is taken into the science buildings we're doing today.
All right, class. So in conclusion, what we've learned today, we've learned what lab ready means, how we need to be designing these buildings. We know that we need to make sure we get the basics right when it comes to safety concerns, as well as drainage, ventilation, all that jazz. We need to make sure, again, that we know our guidance and we're considering continually all the hazards that these sciences might have involved in them. We need to think about the environment that they're around, because these need to be attractive places that people can get to easily so that these scientists can recruit the top talent available to them. We also need to make sure, above all, that our spaces are flexible, because we don't know what the future holds for science, which is exciting. And it is possible to make a sustainable science building. Whew, that's a lot that we learned. Thank you, guys.
Well, thank you, Julia.
Thanks, Julia.
If you want to learn more about Fairhursts Design Group, head over to fairhursts.com. And if you want to stay in the loop on the latest property news, make sure you head on over to placenorthwest.co.uk. And to catch all of our masterclass series, be sure to subscribe wherever you listen to podcasts so that you don't miss a single episode. I'm Julia Hatmaker. Thank you so much for listening.